now that Robin has succeeded in uncoupling ionic liquids and green chemistry, that provides an opening for Phil Jessop to talk green.
All right, thanks very much. And I'll see if I can't put it back together again. So, as a point of background, it's getting infection. All right, so, the point of background, I was asked, was it March? To write a book, a chapter for this IEC book, and I asked about green chemistry, and I asked, okay, when's the deadline? And Martin said, last September. Okay, it might have to be a fast job then. So, yeah, John Warner and I worked together almost as fast as Martin wanted us to, and so this speech is sort of a spin-off of that, although in the chapter I actually just we looked at the 12 principles of green chemistry and did an essay on each one, sort of assessing where it's coming from and some other comments on each of the 12 principles. And I didn't think I would force you to listen to that. I just wanted to give you some perspectives on green chemistry in particular. Well, where does green chemistry come from? And here's a question for you. This is the centennial of the IEC division. 100 years ago, when that division started, was there any green chemistry? And I'll answer that question in a moment. I'm also going to talk about impact reduction strategies, and then what's holding green chemistry back? Why isn't this universal and we're way ahead of where we are now? I'm obviously not satisfied with where we got so far, and I think we should be moving ahead much more quickly. And the question is, why are we not? That's what I wanted to talk about. So first, let's talk about, I believe this one is Manchester, and that one's Pittsburgh, or the other way around. I forgot which one is which now. But these are middle 1900s, and you get the idea that things weren't always completely clean in the industrial world. And people were actually okay with that for many, many years. And that's because pollution equals prosperity. Okay? And I'm not kidding. Smoke means jobs. The cities that have smoke are the cities that have employment for you. Smoke also gets rid of bugs, right? So smoke equals health, right? This was the attitude. People understood that pollution was a necessary part of having a prosperous world. And so why would you want to fight pollution? You should encourage it, right? And then people started having some problems. So they realized that pollution isn't just prosperity, it's also disease. So how are you going to resolve that? What you've got to do is you've got to put some quick fix on the plant so that the pollution doesn't escape the plant. And then you can have your prosperity and have less in the way of health problems. And so pollution prevention became scrubbers, filters, and various expensive things that cost money to the company year after year. And of course, that's not green chemistry. And this way of doing things was the standard until at least the 80s, for a few companies, the 70s. And if you look up the words pollution prevention in SciFinder and ask for hits from before about 1975, everything is scrubber technology and related techniques, not for preventing pollution really, but for creating pollution and then catching it. And that's what pollution prevention meant, was go ahead and make it. And so what we needed to do then is to switch to a new way of thinking which says pollution equals disease, but not prosperity. One of the big criticisms of green chemistry or green anything is that it's more expensive, which of course is not true. But that was the attitude because of lingering beliefs that pollution equals prosperity. If you guys are going to go and shut down polluting plants or causing us to fight pollution, it's going to cost us money, it's going to cost us jobs. So this myth of pollution equals prosperity still is with us today. And so what we've had to do is to get rid of that and go to just pollution equals disease. And the solution to pollution is redesign the process so as not to make pollution. And this actually, thanks to, for one thing, in my opinion, the Presidential Green Chemistry Challenge Awards have been really good at this, is promoting the idea that if you do what would seem to be very logical things to improve the greenness of your process, you actually save buckets of money. And those awards, by publicizing this, and publicizing particularly successful cases of that, have helped to get rid of this myth. So, the question, 100 years ago, in 1908, was there anything in the way of green chemistry? Well, I did a search. The first thing I found out, if you search for green chemistry in SciFinder, and you specified before about 1990, what you mostly get is chemistry of green dyes. But if you look at pollution prevention, then you get all scrubber stuff. But there are occasionally little bits of hope and little flashes of brilliance in the earlier years. And so here's an example from exactly 100 years ago, the year of the birth of the division. 1908, U.S. Geological Survey bulletin by Dwight Randall. I know quite who that person is. And he reported in this that if you change the design of coal burners, you could have energy production with this less smoke. It actually had a drastic decrease in the amount of smoke coming out of these burners by changing the design of the process. That's green chemistry. Of course, they didn't call it green chemistry. But the idea was around a little bit well before the 70s. So for those of you who haven't heard it already, but hope there's nobody in that category, the design of chemical processes products that reduce or eliminate the use and generation of hazardous substances. That is green chemistry. And it's specifically the design. We're trying to look at processes and redesign them so that they will have less impact on the environment. So where has green chemistry been? Well, here's 1908, the Randall paper. I'm not trying to make it look like that's the first green chemistry paper. There are probably others that are earlier. It's just one that I found from exactly 100 years ago. There's the birthday cake for the IEC division. Here are a bunch of bad things that happened, many of which were actually very useful. Probably not to the people involved. But, for example, the Seveso release of dioxins made European regulations become much tighter, and that helps to push European companies towards green chemistry. Silent Spring started a big march towards more and more regulations in the US, and that gave a regulatory push. The American Chemical Society in 1969 actually called for chemistry to be changed to less polluting, or actually non-polluting chemistry, which I thought was a little optimistic. But to give you an idea of the mindset, in 1969, they actually came up with 73 recommendations for how chemists could help to reduce pollution. And only one of the 73 recommendations dealt with changing the process so that it would not make pollution. The other 72 was old school. But at least that one was there. I thought that was promising. 3M started as pollution prevention pays. In Canada, they started responsible care, which a few years later spread over to the US. The word green chemistry, that expression, was first published in 1990, and the Presidential Green Chemistry Challenge Award started in the late 90s, and the Nobel Prize in 2005. The funny thing about the Nobel Prize in 2005, even though it was given for green chemistry, it was given to 3 chemists who had no idea they were doing green chemistry, and had never claimed before that their work was green. And that's the beautiful thing about green chemistry. We can take advantage of all the wonderful work that other people have been doing and make it useful for green chemistry, even if they don't realize that they're contributing. And if you look at the number of papers, here's a number of papers in various different fields, and you can see several different things here. First, supercritical CO2 and biomass conversion got their start in the late 70s. And by start, I mean the flurry of activity where really the number of papers started to take off. Supercritical fluids actually started in 1822. And so it had a long induction period. But ionic liquids, as we just heard, got their big boost around 2000, 2001, and they're just going skyward. If you do that SciFinder search on green chemistry, and you get rid of the stuff about the green dyes, what you'll find is that almost nobody is publishing on green chemistry. The number of papers is quite small. It's just a few thousands. And so the question is, well, how many papers are there out there that are really about green chemistry? And of course, the number must be much larger than that. They're just not mentioning green chemistry in their papers. So I checked, and the people that talk about life cycle analysis, which is the green one, 50% of them mention green chemistry. according to Cyclone, 57 of those pages. In ionic liquids, it's 9%. 9% of the ionic liquid papers mention green chemistry somewhere in the paper, according to Cyclone. For supercritical fluids, supercritical CO2 in particular, it's 0.9%. Less than 1% of those papers mention green chemistry, even though green chemistry is a really good motivation for wanting to use supercritical CO2. So the fact is that green chemistry is being underreported. And that's actually the way it's been for some time. A lot of industry work in terms of getting greater yields with less wastage has been green chemistry, even though it's not been advertised as such. Many areas of green chemistry are currently being studied quite intensively. And tomorrow morning is a session on green metrics that I encourage you to go to. And I just want to look at one particular area, that's chemical substitution. The question is, if you want to make a process greener by substituting something, which of these things are you going to substitute? Well, you remember Bhopal, India? Well, that was a bad intermediate, so substitute the intermediate. What about catalysts? Catalysts are used in such tiny amounts, they don't really need to be substituted, they can never cause any harm, they're only used in micromolar quantities or whatever. Minamata, Japan. And in fact, Joe sort of hinted at this in his lecture. That is a severely deformed young woman, girl, who was born after the village had been polluted with mercury catalyst from the acetaldehyde process. It's dehydration of acetylene. The mercury catalyst was dumped into the bay, and then the fish got contaminated and the people ate the fish. And that happened over 30 years, and even after that catalyst and that mercury was identified as the cause of the problem, it was the cause of the thousands of deaths, the dumping and the process continued for another 10 years before it was shut down. So catalysts can cause very large problems, even though it's very small amounts. Feedstocks and reagents. Well, the usual thing we think of when we talk about green feedstocks, renewable feedstocks, is biomass, and there's a lot of potential there. We should also not forget waste plastic. It is inherently renewable because it's being renewed whether you use it or not, and carbon dioxide. And in fact, if you look at the availability of these renewable feedstocks, carbon dioxide wins. You've got a lot of this stuff. And this is just the amount that's available as a scrubbable material from power plants. This does not include mobile sources, cars, airplanes, trucks, cow fart, whatever. This is just the easily scrubbable stuff. And this is the amount of polyethylene terephthalate that's currently being collected compared to the amount of biomass of the various kinds that could be easily collected. And I got those amounts from a review article on the topic. So when we think about renewable resources, let's not forget the waste polymers and the waste CO2. Because there's lots of chemistry you can do with those things, and there's certainly not of them available. Now, here is just an example of using the biomass. People have been talking in many papers and lectures about using biomass in the future. We're already doing it. In fact, this is one of the great success stories of green chemistry, and even before green chemistry was called that, is the fact that we're using bio-renewable reagents as a source for an enormous range of chemical products, and it's already reality. Substituting a solvent, well, decaffeination of coffee, it used to be methylene chloride, in fact it used to be benzene, not particularly good for you, and then in the 1960s the Germans came up with the supercritical CO2 process, only about 140 years after it was discovered, supercritical fluids that is. And that, of course, is a great leap forward. This is very obvious substitution of something that's obviously not good for the environment versus something that is just about fine. How about this substitution? Substituting water for CO2. They both seem to be rather green, and they're not necessarily. The trick is, if you're going to make, this is a plant for the production of Teflon, on the process. They're polymerizing tetrafluoroethylene. And the process, until this plant was built, used water as a solvent. And because tetrafluoroethylene is not soluble in water, you have to add perfluorooctanoic acid or related surfactants to make it soluble, or at least make an emulsion of it. And it's the existence of, or the requirement for these surfactants that causes the damage. These surfactants show up in breast milk, and they're in you and I, they're all over the world, and DuPont's getting fined on an oppressively frequent basis for that. And so DuPont made this plant using CO2, which doesn't require any surfactants because CO2 dissolves to the polymer very well. And so making a substitution from a green solvent to a green solvent greatly enhanced the greenness of the process. Now my chemical substitution of the product. This is DDT, an absolutely wonderful chemical that saved millions and millions of lives, but has some serious environmental downsides. And this is a problem I believe has still not been completely resolved. How can we save those millions of lives and still not cause environmental problems? So that's an example of a need for product chemical substitution. So what has green chemistry achieved? These are just examples from those Presidential Green Chemistry Challenge Awards, which have been publicized very widely, so I'm not going to read through them or anything, but just get an impression. If we're talking, for some of these processes, quite large reductions in waste materials that have to be bought and then disposed of. So in most of these cases, very large amounts of money have been saved by the companies involved. So that means that the myth of pollution equals prosperity is dying fast, and these examples are helping to kill it. Pollution actually is not prosperity. So the lessons: financial savings, improved product quality. I should mention that that Teflon process using CO2 gives far higher quality product than the process using water. So you get improved product quality, decreased regulatory concerns, increased competitiveness, jobs. Pollution prevention equals prosperity is the new paradigm. So all that's great. So why is it taking so long? What is holding back green technology? That's the kind of vessel that was first used in 1822 by Charles King and de la Tour to discover supercritical fluids in an experiment that would never be approved by safety committees today. And this is the plant where they're using supercritical CO2 to make fluoropolymers. 1990s, 1822. Decaffeination of coffee, 1960s. What took so long? And why is it that now that they've made this plant, they've shown it works on an industrial scale, they've shown the product is higher quality, they're not going to do any more of it? They're not making any more plants. Why? The answer is, first, why are they taking so long? Fear of change. I'm not talking about just primal fear. I'm talking about financial losses if you don't make the right move. Plant managers don't want to jump into new technology unless they're sure it's going to work because millions of dollars are on the line. And the reason why they're not going to continue with these, other than this plant itself, which is going to continue just fine, is overcapacity. If you've got enough capacity for polymers, why are you going to make any more plants? So that's one. Those two factors are holding back green technology. Here's another problem. How much of the energy in gasoline or diesel actually goes into making the truck or the car move forward?
6%.
Yeah, it depends on the vehicle and the kind of fuel, but it's really low. Okay? The vast majority of the energy content in the fuel goes into making your engine block get hot, the exhaust system get hot, and the exhaust gases get hot, which isn't particularly useful. So, there are some limitations in the theory of engine design. It means you can't get a lot more useful motion out of it, but what if you can take this heat and divert it back into motion or to usable energy? That would be huge if we could do that efficiently, right? Well, problem is technological hurdles. What other things are holding back green chemistry or green technology? I should mention that previous problem. My group's working on it. We hope to get over those technological hurdles and report back at another meeting. What else is holding things back? Fine particulates in the cities. People don't like it. People blame industry. People blame trucks. What is the real cause? This is data from Canada, cities in Canada. 37% of the fine particulates found in cities comes from residential power and heat. And of those 37, 36 of them come from people putting logs on the fire. Okay? Take a look at the nasty old trucks. 20% for all transportation, trucks, cars, airplanes, ships, etc. Well, ships while they're in port anyway. Manufacturing, those nasty industries, no, they don't even compare to people putting logs on the fire. But people are confronted with this. In fact, part of California tried to legislate to stop people from putting wood in the fireplace. And now you're trampling on people's rights. They have the right to put wood in the fire. So the problem is public attitude. If it's okay to complain about companies, why isn't it okay to stop the public from doing things that are ungreen? What else is holding back green chemistry? There's dry cleaning equipment. The first dry cleaning solvents were naphtha and benzene with some really obvious flammability problems. So what did they do when they realized that that wasn't tenable? They switched to Stoddard solvent, which is heptane to dodecane, straight chain alkanes. Well, the problem is they're neurotoxins, so they got rid of those and switched to trichloroethylene, which is just plain toxic. And then they switched to carbon tetrachloride, which causes cancer. And then they switched to tetrachloroethylene, which was touted as the new safe solvent. And now we can't use the land that dry cleaners have been taken away from because the ground is contaminated, the workers are dealing with this. When you take dry cleaning home, you're supposed to hang it outside without that plastic wrap for half an hour before you bring it inside your house because it shouldn't be exposed to the tetrachloroethylene. And nobody does that. So what are they doing? What's the problem here? The problem is knee-jerk substitution. Somebody, usually the papers, gets a hold of something and says, this is bad. And they're often right, it is bad. And so what the government does is if they want to look proactive, they ban it right away without checking what the replacement's going to be. Once you do that, you get really stupid decisions made. So knee-jerk substitution is not helping us. And here's an example. When you're cleaning, or not you and I, and the people in the shops that fix cars and fix brakes, when they're cleaning all the oily goo off the brake pads, they use a spray can. The spray can contains tetrachloroethylene. They don't use gas masks, they don't use fume hoods. Cars don't fit well in normal fume hoods, and the workers, at least in California, it's pretty hot. They don't want to wear the gas masks, it's not comfortable. So they're inhaling very large quantities of this. A few years ago, the California government decided to ban tetrachloroethylene for those applications, and so the companies that made these spray cans switched to acetone hexane mix. The problem is, hexane is a neurotoxin. If they used straight hexane, it might not have been so bad. And this problem was discovered by Malcolm Wilson in Berkeley. Hexane's neurotoxicity is multiplied tenfold by the presence of acetone. So what happens, these workers are coming into hospitals unable to control their limbs. They couldn't walk, they couldn't control their arms. And this is within the past 10 years. And the fact that hexane was a neurotoxin was known well before that. And the fact that acetone multiplies the neurotoxicity of hexane was known well before that. Knee-jerk substitution. When governments or other people are going to start calling for the banning of chemicals, they have to consider what the replacement is going to be. So, what's the last thing holding us back? Which factor is going to determine the selection? The old rules were, when you're making a product or a process, efficacy and price are the most important thing. What is the consideration that should now take over from efficacy and price, or at least add to efficacy and price, when you're considering whether a process is green or not? And the answer is media profile. That's the answer. And unfortunately, the governments who are trying to respond to this issue, media profile, are trying to be proactive, and that is good. And I'm facing this problem with the government back in Canada. They're trying to get ahead of the media by solving problems before they arise, and identifying toxic compounds, this kind of thing, and getting rid of them before the papers make it a big issue, so that the governments can appear proactive rather than reactive. But the problem is that they're looking at human toxicity as the overriding issue by which to judge whether a chemical can be banned or not. And that means that we're neglecting all of these other things. They're also neglecting the problem of knee-jerk substitution. So the problems are unclear priorities, or economically driven or media-driven priorities, which direct you to making an overriding consideration for human toxicity and neglecting the other factors. So the hindrance we have is blocking green chemistry, overcapacity, which can be solved by waiting till demand exceeds supply, technological hurdles and lack of alternatives, both of which can be solved by more research, unclear priorities, which means we need people who make policy, green policy, which is more intelligent than knee-jerk substitution. We have conflicting priorities, which means you have to go back to research, public attitude and fear of change, which is not just in the public, but also in the minds of the decision makers in industry, education, and research. Closing thoughts. The basic idea of green chemistry, rethinking the chemistry of industrial processes can reduce impact and increase profit, transfer problems into financial opportunity. Banning chemicals is not sufficient. You have to find acceptable replacements beforehand. And consumer education is absolutely vital because consumer practices can have a larger impact than industrial practices. So blaming industry or even fixing industry isn't good enough. Thank you very much.